has a BS degree in chemistry from the University of Cincinnati and an MS in environmental engineering from Oregon Health and Science University with a professional hydrology certification from the American Institute of Hydrology. Mr. Bellingham started his professional career working as a chemical engineer in Ohio before pursuing an advanced degree in environmental engineering. While in graduate school, Mr. Bellingham focused on watershed hydrology and geochemistry. In 2006, he became the soil scientist at Stevens Water Monitoring Systems, responsible for developing sensor methods and technology for soil. Currently, he works in business development in the areas of water resource, working towards finding systems and modeling-based solutions for challenges facing water and soil resources. Please join me in welcoming.
Thank you. Thanks for attending. So the title of my talk is Improved Water Supply Forecast Using Soil Moisture Data. And we published this paper last year, my colleague and I, who could be here, Jolene Lee from the USDA. And so these first couple slides are a bit of a background on what I'm going to talk about today. And roughly 80% of the water consumed in the United States and also around the world is used for irrigation and food production. And in the western United States, this water is distributed by irrigation districts and U.S. Bureau of Reclamation. And I have a couple slides here showing some stream diversions for wholesale water usage in some irrigation districts. Also, hydroelectric power is very common, particularly in the western states. In the state of Washington uses nearly 80% of the electricity in the state of Washington is hydroelectric, as well as in Oregon and Idaho. Most of the electricity comes from dams and hydroelectricity. And so, looking at some of the environmental impacts of the consumption of natural waters, we see issues like temperature loading, salinity loading, flow conditions, various water quality issues associated with this kind of consumption. And dams, the main issue here is flow conditions. If a dam needs to provide more electricity, they can't exactly send a tsunami downstream and vice versa. So with that, there's some major economic drivers associated with the forecast of the available water. And so the forecast of available water in our natural waterways in the western United States, this addresses things like flood risks, energy trading for hydroelectric, and water for irrigation districts and irrigation and food production. And so in the western United States, most of the available water originates as snowpack. And so some of the snowpack can get quite deep. Most of the surface water and groundwater is recharged from this seasonal snowpack that occurs. And here's just a Google Earth shot of some of the mountain ranges, particularly the Cascades, that receive quite a bit of snowpack in the winter months. And so one of the main parameters used to quantify the snowpack is a parameter called the snow water equivalent. This is essentially how much water is in the snow. So when snow falls, it goes through different melting regimes and throughout the season, and the amount of water that's available in the snowpack can be quantified through the snow water equivalent, which is measured with one of these snow tubes. And so, starting about 100 years ago, the relationship between the amount of snow and the stream flow was started to become characterized. The father of this research is James Church at the University of Nevada. And today, this is carried out by the SNOTEL network, which is operated by the NRCS. And so the SNOTEL network has about 900 sites in 12 states. And these SNOTEL sites measure the snow, measure the meteorological parameters in these alpine areas, and use that data to forecast the available water at various strategic locations, on streams and rivers and reservoirs. And this is another related network that the USDA also operates, called the SCAN network, which also has several hundred sites in the United States and Antarctica and a couple territories as well. So this is a typical SNOTEL site. We see here, this is called a rocket gauge. And this is a total precip gauge. So all of the precip, snow or rain or whatever, goes into this orifice up top. It melts through an antifreeze solution that's in the base, and there are highly sensitive pressure transducers that can measure the total precip throughout the season. These little baffles up here normalize the wind above the orifice, so you get a more normalized reading. This here, this is what's called a snow pillow. So snow will pile up on this bladder and send fluid up this standpipe here. And so based on the fluid level in the standpipe, you can get a SWE, or snow water equivalent measurement. This sensor here is a radar sensor that measures the snow depth throughout the snow year. And then this building here is, contains the data logger and some of the telemetry that's used. And this is some more slides of various SNOTEL sites, and snow pillows. And so the SNOTEL program started implementing the Stevens hydroprobe soil sensor into the network to measure the soil water content in those snow courses and for further forecasting. It was recognized that soil contains a major reservoir for water in alpine areas. So if understanding of how much water is in that reservoir, the forecast could be improved if that was implemented. And so the current forecast is a principal component statistical relationship, and this is a simplified version of it, but basically you have the input parameters, which are the antecedent stream flow from previous years, fall and winter precipitation, spring precipitation, high and low altitude snow water equivalent. And so these are the input parameters, and so the output parameter is a totalization, so total stream flow in acre feet for a certain time frame. And this is an example of what a forecast product looks like. And this is available to the general public on the NRCS website. And so we have, it's a statistical exceedance product. And so, for example, if you have a 90% chance you're going to exceed 255 acre feet in this time frame at this particular USGS reference site. And so you can, and these forecasts are issued on a regular basis, seasonally and monthly, for the general public and also scientists and energy traders and irrigation districts alike. And so, as I mentioned, water is a significant reservoir for water in a watershed. And so characterization of how much water the soil can hold would be a pretty important parameter in this forecasting model. And so what we want to do is we want to add a soil moisture component into this principal component model for forecasting to see if we can improve it. And so the goal of this research is to run the simulations, add the soil moisture component, and see how much better the forecast can be if we implement the soil moisture component into the model. And so our study area is in Idaho. It's a reference point on the Boise River. This is a USGS stream gauging station There's 3 snow-tail sites we looked at in this basin: Jackson Peak, Atlanta Summit, and Bogus Basin. And on the map here, this is all the snow-tail sites in the state of Idaho. And our reference point is the Boise River, just east of Boise, Idaho, in this watershed, about right here. This is a kind of a Google Earth map of it. Here you see Boise, Idaho. Boise River comes up right here. This is right about here is our USGS stream gauging station, which is our reference point. These snow-tail sites, Jackson Peak, Atlanta, and Bogus Basin, they are in the alpine areas where the snowpack occurs in this watershed. And so, as I mentioned, the Stevens Hydroprobe, manufactured by Stevens Water Monitoring Systems, is the soil sensor used in this network. And my company, Stevens Water, we're committed to helping the NRCS fulfill their mission, which is providing high-quality data for these forecasters in this water supply forecast. And so I'm going to skip over a couple slides here. So before we continue, I just want to maybe explain a little bit about soil physics and what we're doing here. And so in soil, or in water in general, there's a phenomenon called capillary forces. And it's the capillary forces is the force that holds water in the soil. And capillary forces results from the surface tension of water at the air-water interface. So from a chemical perspective, water is a very polar molecule, and air is essentially a non-polar. And so the water wants to get away from the air, and so a tension develops at the air-water interface. And we see this in a meniscus. This is why a meniscus occurs. There's surface tension, and the water wants to relax and it climbs the walls of a capillary. And so the same thing happens in the soil. In the soil, there's microscopic pore throats. The water will get itself into the smaller pore throats to eliminate that surface tension. And that's essentially the force that holds the water in the soil. And so we can move to this graph here. On the x-axis here, we have soil type. So as you move to the right, you get more clay-rich. On the y-axis here, you have soil moisture. And so as you get more clay-rich, the soil water retention characteristics change. We have a parameter called the field capacity. And the field capacity is the point at which the capillary forces can no longer hold the water in the soil. The soil gets so saturated or wets up to a point where gravity can then exceed capillary forces and then pull the water downward. And so this is called a soil water retention curve. And so here you have on the y-axis, soil moisture is a fraction. And on the x-axis, you have the unsaturated matrix head of the soil. And what that is that's the amount of pressure it takes to pull water out of soil. And so this is called a soil water retention curve. And of course, it changes with soil type. So and this curve also has inflection points. And so one of the inflection points and the slope of that inflection point is what's called the field capacity. And again, that's where the gravity and the capillary forces sort of equal one another, and that's the point at which water in the soil will flow downward and recharge the saturated zone. And also, it's important to note that from this curve, you can infer a lot of things. You can take the inflection points, the slope of these inflection points on this curve, and calculate things like the unsaturated hydraulic conductivity and other hydrological parameters that allow you to get the infiltration rate and volumetric flux of the soil. And so we characterize the soil at each of these 3 snow-tail sites. And so the last column